Albertian Institute of Science and Technology. Make engineers, not just engineering graduates.
Hi all, myself Alvin D. Xavier, Department of Mechanical Engineering, Albertian Institute of Science and Technology, Kalamassery. Today we are going through the topic 2D transformation from the subject Computer Aided Design and Analysis for the 6th semester Mechanical Engineering students KTU. So dear students, today we are going through the topic 2D transformation. (2D) transformation means the movement of 2D objects like triangle, square, rectangle or circle from one parts of a display to the other parts of a display. That is known as 2D transformation. Basically, 2D transformations can be classified into three categories. First one is translation. Second one is scaling. Third one is reflection. So first we are going through the topic 2D translation. As the name indicates, the translation means the movement of an object. Here I am considering a square. So this square can be moved in three different ways. One is in x-axis, one is in y-axis, and another is in both x and y axis. So in computer graphics, we are using an algorithm by matrix method. The coordinates is 1, 1, here 2, 1, it is 2, 2, and it is 1, 2. So I already said this is a square with unit length, and coordinates are 1, 1, 2, 1, 2, 2, 1, 2. So when I am shifting this square in x axis or x direction, the important thing is that only the x coordinates will change. Suppose I am shifting this square in x direction by 3 units. So square will be like this, and I am shifting in 3 units. That means this coordinates change from 1 to 4 for the point A. So this will be 4, 1. Like that, the point B will shift from 2, 1 to 5, 1. And here it will be 5, 2, and it will be 4, 2. So in this method, we are using the shifting of the square in x direction. The important thing is that only the x coordinates change and there is no change in y coordinates. So I already said that we are using the matrix method for this method. For that, matrix xy is equal to, I am denoting the coordinates in matrix form: 1, 1, 2, 1, 2, 2, 1, 2. So this is the xy coordinates of the initial square. In order to get the final matrix, I am just adding another matrix. That matrix is known as translation matrix, represented by capital T. So what is capital T? I already said that we are just adding the x coordinates by 3 units. I am shifting this square in 3 units, only in x direction. So I am just adding the 3. This is translation matrix. That matrix have x coordinates and y coordinates, and only the x coordinates have values 3 and all y coordinates is 0. The resultant will be 4, 5, 5, 4, 4, 5, 5, 4, then 1, 1, 2, 2. So the resultant matrix is the collection of all the coordinates of a square. So this is the logic behind, or this is the algorithm behind the translation of any objects. This method can be used for a triangle or rectangle, even for a circle. So this is the basic principle or basic idea behind the translation of any 2D objects. Now we are going to study the 2D transformation in y direction. So this is the diagram that we drawn previously. I am going to move or shift this square in y direction. So important thing is that there is no change in the x coordinates, only the y coordinates change. I am going to shift this diagram, suppose 2 units in y direction. So the coordinate is 1 1, 2 1, 2 2, 1 2. So the initial matrix x y is 1 1, 2 1, 2 2, 1 2. I am going to add a translation matrix T, capital T. That means in this we are shifting this object in y direction. That means we are adding units, 2 units in each y coordinates, and there is no change in the x coordinates. So the adding matrix will have all the x coordinates 0. Then I am adding 2 units in y coordinates, just opposite of the previous example. The resultant will be denoted by x dash and y dash is equal to 1 2 2 1 and 3 3 4 4, 3 3 4 4. That means what is the change in this? Only the y coordinates change. That means this diagram will go like this. They shifted to the only in y direction. Similarly, we can translate this diagram both in x and y direction. Then what will happen? Nothing will change. There will be no zeros in the translation matrix. Suppose I am going to change this matrix in 3 units in x direction and 2 units in y direction. I am just combining the previous 2 examples into one example. In the first example, we translated the object in x direction by 3 units, and second example we translate the object in y direction by 2 units. In the third example, or in this example, I am combining the both 1 and 2. That means I am combining both 1 and 2, then so this is our starting matrix, initial matrix. We know that 1 1, 2 1, 2 2, 1 2, and adding in x direction by 3 units and in y direction by 2 units. This is the translation matrix. Then the resultant x dash y dash is equal to 4 5 5 4 and 3 3 4 4. The important thing is that what will be the resultant image of this diagram? That is very important. Then we will get the clear idea of the 2D translation both in x and y direction. This was our initial matrix. When we shifted this matrix in only in x direction, the matrix shifted to this position, and when we move this diagram in y direction only, then we will get the rectangle in upward direction. When we shifted in both x and y direction, we got like this. That means the rectangle moved both in x and y direction or simply the rectangle moved in a 45 degree. So this is the basic idea behind the 2D translation. Translation can be of three types: in x direction, in y direction, and both x and y direction. So our next topic is 2D scaling. So what is the need of a scaling? The scaling method we are used in zoom in and zoom out application of a computer graphics. So this is the basic algorithm behind the zoom in and zoom out application. So we are again start with an example. Our square 1 1 2 1 2 2 1 2. So scaling means we are enlarging and or reducing an object. Enlarging means zoom in and reducing means zoom out. So in order to get the final coordinates, so these are the 1 1 2 1 2 2 1 2 are the initial coordinates of the rectangle. In order to draw the final rectangle, we have to get the final coordinates. So in order to get the final coordinates x dash y dash, we have to multiply the initial coordinates with a matrix known as scaling matrix. That's a very important thing, scaling matrix. Okay. So for enlarging this square, the scaling matrix will be greater than 1. In order to reduce this diagram, the scaling matrix will less than 1. So that's very important. So scaling matrix will be greater than 1 for any enlargement of object. Scaling matrix will be less than 1 any reducement of the object. Okay. So we will go through. So our xy matrix are 1 1 2 1 2 2 1 2. I am going to enlarge this diagram. So now the length of each side is 1. I am going to enlarge to double this size. So it will become a bigger square with the side 2 2 2 2. So how we get that? So in order to get the final coordinates x dash y dash, we have to multiply with the initial coordinates with the scaling matrix. Then what is scaling matrix? I am going to double this diagram. So we have to multiply with the matrix 2 0 0 2, where 2 denotes the how much degree of enlargement we need. We are going to double the size, so we add 2 0 0 2. Then after the multiplication we will get 2 2 4 2 4 4 2 4. So this is the final coordinates of the resultant matrix. So I am going to draw that one with the figure. So this is our initial diagram. Then next diagram will be, this is 1 1 2 1 2 2 1 2. Our final coordinates are 2 2. So this is our starting point or first point. Then 4 2. It will be like here 4 2. Then 4 4. So I am going to coincide this. Then 4 2 I already drawn. Then 4 4. Then 2 4. 2 4. So by scaling matrix we enlarged a square with unit 1 length to the unit 2 unit length. So, this is the basic idea of the 2D scaling. Similarly, we can also reduce this rectangle to a smaller size like this with a scaling factor of 0.5 or 1 by 2. In order to get that, we have to multiply with the scaling matrix 0.5, 0, 0, 0.5. So, it is as simple as that. In order to get the final coordinates of a scaling matrix, just multiply with the matrix scaling matrix. In order to get the final coordinates of the matrix, a rectangle or a 2D object, we have to multiply it with the scaling matrix. Okay. So, we are going through the third transformation, that is 2D reflection. Most interesting type of transformation is 2D reflection. Then what is reflection? Reflection means to produce a mirror image with respect to any axis or baseline. And 2D reflection is of three types. One is reflection about x-axis, reflection about y-axis, reflection about origin, or both x, y axis. So, again we are going through an example. I am going to draw a 4-quadrant system, then it will be more clear. Consider a triangle like this, and this is x-axis, y-axis, origin. The reflection about x-axis means, suppose consider we are putting a mirror here, then we will get a mirror image on that mirror. So, that means the reflection about x-axis means the mirror image of this object, and it will be like this. So, this is the reflection about x-axis. Then reflection about y-axis, it will be like this. That means we are putting a mirror here. Then reflection about origin or reflection both x and y-axis, it will be like this. So, there are three types of reflection are there: reflection about x-axis, reflection about y-axis, and reflection about origin. Then we are going through, this is the pictorial representation, then we are going through the matrix formation of this method. First one, reflection about x-axis. Okay, then please look at the figure. I am going to note the coordinates 1, 1, 2, 1, and it will be 1, 2. Please look onto the figure. In this figure, after the reflection about x-axis, there is no change in the x value of this object. Here the values are 1 minus 1, 2 minus 1. It will be 1 minus 2. What happened? There is a change in only the y coordinates, or simply we are multiplying the y coordinates with minus 1. So, in matrix form, so this is our initial coordinates 1, 1, 2, 1, and 1, 2. In order to get the coordinates, final coordinates of the object which reflected about x-axis, we have to multiply it with 1, 0, 0, minus 1. So, this matrix is known as reflection matrix represented by R. Then after multiplication of these matrices, we will get y coordinates with all negative. So, this is the this is the final coordinates of the matrix which is reflected about x-axis. So, in order to get the negative value for all the y, we have to multiply with this matrix. That is a very important thing, that is known as reflection matrix. So, we are going through the third transformation, that is 2D reflection. Most interesting type of transformation is 2D reflection. Then what is reflection? Reflection means to produce a mirror image with respect to any axis or baseline. And 2D reflection is of three types. One is reflection about x-axis, reflection about y-axis, reflection about origin, or both x, y axis. So, again we are going through an example. I am going to draw a 4-quadrant system, then it will be more clear. Consider a triangle like this, and this is x-axis, y-axis, origin. The reflection about x-axis means, suppose consider we are putting a mirror here, then we will get a mirror image on that mirror. So, that means the reflection about x-axis means the mirror image of this object, and it will be like this. So, this is the reflection about x-axis. Then reflection about y-axis, it will be like this. That means we are putting a mirror here. Then reflection about origin, or reflection both x and y axis, it will be like this. So, there are three types of reflection are there: reflection about x axis, reflection about y axis, and reflection about origin. Then we are going through, this is the pictorial representation, then we are going through the matrix formation of this method. First one, reflection about x axis. Okay, then please look at the figure. I am going to note the coordinates 1 1, 2 1, and it will be 1 2. Please look onto the figure. In this figure, after the reflection about x-axis, there is no change in the x value of this object. Here the values are 1 minus 1, 2 minus 1. It will be 1 minus 2. What happened? There is a change in only the y coordinates, or simply we are multiplying the y coordinates with minus 1. So, in matrix form, so this is our initial coordinates 1 1, 2 1, and 1 2. In order to get the coordinates, final coordinates of the object which reflected about x-axis, we have to multiply it with 1 0 0 minus 1. So, this matrix is known as reflection matrix represented by R. Then after multiplication of these matrices, we will get y coordinates with all negative. So, this is the this is the final coordinates of the matrix which is reflected about x-axis. So, in order to get the negative value for all the y, we have to multiply with this matrix. That is a very important thing, that is known as reflection matrix. Now we are going through the reflection about y-axis. Means there is a, suppose that there is a mirror in the y-axis, then we will get a mirror image like this. So, then what is the change in between these two figures? That is very important. In this figure, all the coordinates are positive because it is in first quadrant. In this figure, the coordinates are changed, but only the x coordinates change, there is no change in the y coordinates. Suppose minus 1, 1, minus 1, 2, minus 2, 1. So, difference between the previous example and this example is that in the previous example there is a change in the y coordinates, but in this example there is change in x coordinates. So, we are going with the matrix formation. The initial matrix x, y is 1, 1, 2, 1, 1, 2. So, in order to get the mirror image about y, all the x coordinates will be negative. For that, we have to multiply with a matrix minus 1, 0, 0, 1. Then the resultant will be minus 1, minus 2, minus 1, 1, 1, 2. All the x coordinates will be negative. Then it will be we will get a mirror image about y axis. So, the important thing is that the reflection matrix. In the previous case, the minus sign was in this one with this one, but in this diagram, in this example, the minus sign is above the matrix, which shows that we are going to produce, or we have to get the x coordinate should be negative. Okay. In the next diagram or the next example, we have to get a mirror image about origin. Then it will be like this. So, in this diagram, both the x coordinates and y coordinates will become negative. It will be minus 1, minus 1. It will be minus 2, minus 1, and it will be minus 1, minus 2. So, both the x axis and y axis become negative. That means we have to multiply with the initial matrix, that is 1, 1, 1, 2, 2, 1 become the reflection matrix minus 1, 0, 0, minus 1. The resultant will be all negative matrix minus 1, minus 1, minus 2, minus 1, minus 2, minus 1. So, these are the three different types of reflection about x axis. In that, all the y coordinates will become negative. In second case, reflection about y axis, all the x coordinate will become negative, and reflection about origin, all the x and y coordinates will become negative. So, these are the three different types of reflection. In this video, we passed through the three different transformation. First one, the translation. Translation was moving of object from one portion to another. Second one, scaling. Scaling means enlargement of an object, and the last one is reflection. Hope that the video benefits you. Thanks for watching.